Welcome back. This is probably the last lecture on atomic force microscopy. We have already spent 4 hours discussing different aspects of atomic force microscope. So, I understand now you are a little well conversant with the instrument. You understand what are the critical hardware components or elements of the instrument, and you also understand how I have sort of discussed in somewhat detail about the 2 primary modes by which an atomic force microscope sort of scans or generates the information about a surface, and they are, if you remember, the contact mode, which is the most simple and the conventional mode of imaging, and the intermittent contact or tapping mode. We have also talked about the non-contact mode in somewhat detail. Now, as you have realized, or we have repeatedly we have been mentioning or discussing, that unlike other microscopes where an image of the sample to be scanned under a great deal of higher magnification is taken, in an atomic force microscope a probe actually goes to the surface and picks up the point by point information about the topography and reconstructs it based on data rendering to generate your image. So, as the probe actually physically visits or physically comes in contact in most of the cases, or even in non-contact mode is in proximal contact with the is in proximity to the surface. So, in addition to the topography or how the surface looks, a whole lot of other informations can also be sort of acquired from these measurements, or even performing the atomic force microscopy, or some of them can be sort of just comes as an auxiliary output of the normal or the standard modes like contact mode imaging or tapping or intermittent contact mode imaging. Some of the modes can be sort of, some of these additional informations can be extracted under certain specific conditions. For example, examples of which include magnetic force microscopy or electrical force microscopy. These are type of very specific microscopy tools which can be sort of used to identify different domains with different magnetic orientations or electrical charge or electrical property. For example, if you look at a computer hardware or an erstwhile old floppy disk, these are magnetic storage medias, but topographically they are absolutely flat. There is no topographic contrast. So, if you see it under any standard microscope, including a scanning electron microscope, or if you do a normal routine contact mode imaging scan with an atomic force microscope, what you will see that it is most likely a completely flat substrate. But under MFM, for example, magnetic force microscopy, which is not a direct output of any one of the modes like contact mode or intermittent contact mode, but certain specific arrangements, specialized tips, etc., needs to be used, it becomes possible to identify these magnetic domains. So, this is what is called as the secondary imaging modes. There are a whole lot of things that can be done, and also before I forget, I must mention that in addition to imaging, the rastering action can also be to some extent used as a patterning technique, as one of the direct write patterning technique, and in most cases this is what is known as or referred to as the DPN or the dip pen nanolithography operation. So, we will talk about some of these and some of the secondary imaging modes of an atomic force microscope. Okay. So, we have already so here are some of the informations about or some of the modes that the atomic force the secondary atomic force microscope imaging modes are. So, they are lateral force microscopy, and we also have a small list of the functionalities. We have phase imaging, we have force modulation microscopy, pulse force mode, etc. Then we have magnetic force microscope and electrical force microscope. Particularly, we will pick up lateral force microscopy, phase imaging. These two are interesting because they are direct offshoots of the contact mode and the intermittent contact mode imaging. No additional mechanism or nothing needs to be done. These informations just come out, and any sort of standard or conventional or commercially available instrument. If you are doing contact mode imaging, you will get the lateral force or the friction force image straight away. If you are doing an intermediate contact or a tapping mode imaging, you will get the information about phase imaging. We will discuss in little bit of detail what they are. Then we will talk about a little bit about the force modulation microscopy, which requires an additional pulsation or an oscillation during contact mode. So, this is distinct from tapping mode or non-contact mode, which sort of gives about the local elastic property of a surface. We will not talk about the pulse force mode. This is some sort of an extension about the force modulation microscopy. So, anyone who is interested can sort of figure out what this is. Then we will I'll try to give you some glimpse about the magnetic force microscope and the electrical force microscopy. Both of them sort of have very similar operating principles. They sort of involve a contact mode scan as well as a non-contact mode scan, and then one has to do some bit of clever subtraction of the scans you get to identify the different domains. They rely on the fact that different forces in proximity to the surface have different scaling properties, and therefore, they are different. So, we will see how it looks like. Then there can be other types of microscopy like thermal resistance microscopy, nano indentation and scratching, and then we will discuss this bit a little bit in detail. Dip pen nanolithography for patterning of surfaces. Okay. One can we mentioned that one can also measure the force between a surface and between two surfaces using an AFM. So, I will try to give you an example where these forces can be measured, and we will see that the colloidal probes we talked a couple of classes before plays an important role in measurement of these forces. So, what is lateral force microscope? It's very simply put, it's as follows. As you are dragging, as during the raster action, as you are dragging your cantilever tip along a particular surface. So, what happens is at every instance of time, as the sort of tip visits any specific point, depending on the adhesiveness of the material, there is a force of adhesion between the tip and the surface. Okay. Now, this nature of adhesion and it has to drag. So, from one point to the other, it travels along the surface. We have already talked about contact mode. So, this travel from one point to the other, it's the surface, the tip is dragging along the surface. So, there is a dynamic friction between the tip and the surface. Now, you understand, if we have a different domain, a domain of a different material, or let us say a different phase on the surface, then what will happen? The frictional property over here, let us say the phase 1 and the phase 2 will be different. Therefore, when the piezo sort of applies the same voltage for a motion in the x direction by manipulating the x plus and x minus components of the piezo, we already have talked about all these things. What happens is, under the same force, the extent of local adhesion or the local friction between the tip and the surface becomes different, or becomes a function of the phase or the domain. Or in other words, if this is your cantilever from the top, because of localized friction, let us say it is sort of there is a lateral distortion or lateral movement of the tip along this, because what is happening when you are dragging the tip, here the tip is in contact, the sort of piezo moves from this direction where it is mounted. So, this follows or drags like this. So, to what extent there is going to be this lateral torsion or twisting is a function of the friction properties. So, if over this zone and this zone the frictional properties or the level of adhesion are different, then what is going to happen? The extent of twisting over the zone 1 and the extent of twisting over zone 2 will be different. So, it is something like this what is shown here. So, if this is the sort of the lateral displacement or deflection over this particular zone, let us say zone 1, since the surface properties also affect the friction properties as well as the adhesion, the extent of lateral distortion or lateral deflection is different on the phase 2. Therefore, in addition to the standard topographic contrast, you also get an additional contrast in terms of due to this lateral distortion, and which correlates essentially to the localized friction and adhesion properties. Okay. So, in this way you can map different components of composites or different domains of block copolymers or blends on a surface, even when there might be no topography. So, you can have situations where there is the topography looks perfectly flat, but you can find out that there are different domains which appear in the friction image or the lateral force contrast. So, this gives you an idea that this is a surface which is flat, but there can be different domains on the surface. And this contrast generates does not get reflected in the topographic image. So, this contrast, no contrast in the topographic image, but the contrast is manifested in the phase image. Okay. So, this is what is lateral force microscopy. This gives you some sort of an idea about the extent of twisting, you can say, depending on one location to the other. I would say that every location, because of this motion. So, you have I will repeat the figure, you have this is the cantilever, you are looking from the top, your tip is below this one. So, you can't see it from here, but the tip is below this one and touching the surface. On this side it is mounted to the piezo scanner. So, as a part of rastering, the voltage is given here to manipulate the x plus and x minus. So, this tries to move, and the location where the tip is in contact with the surface, because of the friction, static friction, this tries to hold back. So, this movement has an intermediate configuration like this, or there is a time delay, you can say. Okay. Now, this extent of whatever is the delay or this deformation or deflection in the lateral direction, whatever that is, that becomes now a function of the local friction or adhesion on the surface. So, if a surface has higher level of friction or the frictional opposition to movement of the tip along the surface, or there is a domain which has higher friction, offers higher friction, or is more adhesive, then the extent of the lateral displacement or the lateral distortion will be higher. So, in that case delta 2 will be higher than delta 1, and if there are distinct domains on the surface which have different friction or adhesion properties, of course, this will show up as an additional contrast in the phase image. So, this is all about lateral force microscopy, a very powerful tool to identify different domains, particularly useful in analyzing composites, blends and block copolymers. And exactly, so the other important aspect, when we were talking about the microcontact printing, I showed this image, if you remember 5-6 classes before, and we showed that I will discuss this in detail. So, microcontact printing, if you remember, we talked about making of a surface which is chemically patterned. So, there is no topography, there is virtually a flat surface, but you have isolated domains here which have, let us say, higher or lower surface energy. But topographically this is flat, but we know that since we have microcontact printed it. So, these are surfaces where these are areas where the surface tension is gamma 1, these are areas where the surface tension is gamma 2. So, change in surface tension also also results in change in local friction or adhesion property. Okay. So, now when you do a good contacts mode scan, these are, if you remember, these are self assembled monolayers. So, these are one molecular layer thick, which is sub nanometer. So, topography wise it is nearly flat, right, but you have these domains which have different surface properties, the friction property, surface tension, adhesion, they are different. So, what would you expect? You would expect that your topographic image will be perfectly flat, but this, now you understand that this contrast will be visible in your phase image, and look at this image set now. It is exactly the same thing. So, this is the topography image or essentially the deflection image, where it is nearly flat, but you see this is the friction image, and you very clearly see the presence of the stripes, which are the different wettability regimes. What you need to understand, that this friction image, of course, you know how the image has been generated. So, it has been rendered brighter and darker zones. What you cannot say is, looking at this image, is whether the brighter zones or the darker zones corresponds to the gamma 1 areas or gamma 2 areas. This is something you can't say looking at the image. What you must understand, that this gives you an idea that there are some domains which has difference in surface properties. It can be friction, it can be adhesion, it can be surface tension, whatever. But whether the darker one or the brighter one corresponds to the higher surface energy or lower surface energy, you can't directly correlate. What you can correlate, you can look at the amount of voltage that is necessary, and based on that you can identify the domain which offers more resistance. The black one offers more resistance for the tip to move on, or it has got higher level of friction, that you can tell. But you must have some physical idea about what happens after you coat this surface with a SAM layer and how the friction gets altered. So, this is some application of lateral force microscopy. An exact equivalent of lateral force microscopy in intermediate contact or tapping mode is the phase imaging, which essentially is phase imaging monitors the phase lag between the signal that drives the cantilever. So, we understand that in non-contact mode as well as in intermittent contact mode, there is an additional drive that sort of oscillates the cantilever like this, what you know here. So, what happens here, due to the localized friction, there was a lateral deflection or twisting of the cantilever. What happens here, it is continuously oscillating, and in intermediate contact it is sort of tapping the surface. Now, depending on the adhesiveness here, so this is, let us say, the input cycle, input pulse that is going on, sort of that is oscillating the cantilever. Now, depending on the nature of the extent or the extent of local adhesion, there might be a delay, time delay or a phase lag between the input signal and output signal. So, this is like for a nano or picosecond as the surface sort of taps, it is in local contact. So, it is sort of, you can argue that this is some sort of a local holding time. It is like due to the extent of due to the effect of adhesion, it is sort of locally held for a fraction of a second or a millisecond or a picosecond. Now, if the whole surface is made up of the same material, then what will happen? Of course, this whatever is the time delay, it is going to be same all over the surface, and therefore, the phase lag or the phase lag in the sense that phase lag of the between the input signal and the output signal, the phase lag between the input signal and the output signal is going to be uniform all over the surface. However, now again the same thing, if you have different domains on the surface. So, this is, let us say, domain 2 and this is domain 1. So, what will happen, because of the surface properties are different, they are this local holding time or the extent of which is sort of a measure of the extent of adhesion is going to be different. So, over here if that delay or that lag is by let us say an amount phi 1 degrees, over here the lag might be phi 2 degrees. So, there will be an additional contrast along with the topography gets generated based on the phase lag between the input signal and output signal. Okay. So, it is like this. So, you see let us say this green line is the input signal and the dotted line is the output signal. So, you can see there is a phase lag. Now, the cantilever sort of encounters a different zone, let us say zone 2, which let us say has higher level of adhesion. So, therefore, the phase lag increases. So, it can be sort of used for mapping of different composites different components in a composite material, different regions of high and low surface adhesion or hardness. In many cases phase imaging complements lateral force microscope and force modulation microscope, something which we are going to talk in a little detail. Phase imaging is fast and easy to use tapping mode with AFM and with all the benefits of imaging soft adhesive and loosely bound samples. So, this is a very nice extension. So, you do not have to do anything really, no additional fixture or nothing is required, but all you need to do, or this phase image is sort of comes as an auxiliary output to the standard intermittent contact or tapping mode. This is couple of examples. So, this is a how subsurface structures can be sort of imaged using based on the phase imaging. So, this is a special example where we had a sort of a holy surface. So, surface had some holes and which was covered with a thin polymer film like this. So, how the sample was prepared and all that we are skipping the detail. So, what we had was these holes were covered with the polymer film, which was about 40 nanometer thick in this particular case. This is an example from our own work in our group. So, it's a very nice example, demonstrates the strength of phase imaging. So, if you look at the topography, of course, these areas are flat. These are some of the areas where the film has already ruptured over the hole and therefore, you can see the hole. So, there is nothing great, but over this area you have a feeling that the surface is completely flat, and which is also the case. But since there is a difference between let us say this area and this area, because over this area when the cantilever taps, it is actually tapping on the surface on a film which is coated on the substrate. In contrast, when it taps over this particular area, it is because it is tapping over here at this surface, it is tapping at a film which is self standing, which is sitting on a hollow cylindrical opening or something like that. So, therefore, the phase lag between the input and output signal over this area and over this area will be significantly different, and precisely that you can see now in the phase contrast image. So, this part of the film which topography shows that it is perfectly flat, there is nothing. In the phase contrast image you see that it beautifully shows the subsurface holes. So, this is one of the strengths of phase contrast imaging. Similarly, you can have a film, a thick film which is coated on a surface which contain these type of random structures, on that a polymer film has been coated which is perfectly flat. So, we in one of our earlier lectures have talked about coating of a polymer film on a structured surface, and we also argued that if the film thickness is adequately thick in comparison to the height of the features, then the film can be flat. So, this is a perfect example of that. Topography shows that the film is very flat. However, when you look at the phase can pick up these subsurface structures. The idea is very clear here. It is tapping over a film which has a local thickness of let us say H1. In contrast, here because of the surface features, it is tapping over a film which has film thickness of H2. So, there is a difference between the level of stiffness of the film over the two zones, and which is aptly manifested in the phase contrast image. So, these are some examples of phase imaging. The third mode what we are going to talk today is another secondary imaging mode, but this one has to sort of work out additionally with some additional fixtures or additional input. It does not really come out free like lateral force microscopy or phase contrast image is the force modulation microscopy. What is done in force modulation mode, the tip it is essentially a continuation of contact mode. In force modulation mode, the tip is scanned in contact with the sample, and the Z feedback loop maintains a constant cantilever deflection. So, as what is done in a contact mode AFM. Further, a periodic vertical oscillatory signal is applied to either the tip or the sample. Now, the amplitude of the cantilever modulation that results from this applied signal varies according to the elastic properties of the sample. What it means? It is something like this. So, you are doing a contact mode imaging, and now you are giving an additional oscillation. Now, depending on how flexible or how elastic or soft your surface domains are. So, if you encounter a soft zone, softer zone, what will happen? This modulation frequency or this additional oscillation you have given, this will allow the tip to sort of penetrate or deform this softer regions. In contrast, if it now encounters a hard or a stiff region, it will not be able to sort of deform it, and therefore, there will be a difference in the output signal of this additional oscillation that you have given over a hard and a soft region. So, in hard region, the amplitude of the output oscillation will be almost same as that of the input oscillation. However, over a soft region, a part of this oscillation will get damped or get dissipated over the softer zones, and the output signal will be much shorter amplitude. So, this can be sort of transferred into an additional contrast to generate what is the main role of FMM, force modulation microscopy. So, from the change in the amplitude of the cantilever modulation, the system generates a force modulation image, which essentially is nothing but a map of the sample's elastic property. So, you can map the elastic property, the local elastic property of a specific surface with the nanometer scale lateral resolution with force modulation microscopy. So, next we come to the other class of techniques. These are particularly EFM and MFM I should focus, I should mention, that is the electrical force microscopy and magnetic force microscopy. These are very unique techniques which sort of allows you to identify either distinct electrical domains based on long range Coulomb forces by taking advantage of the Coulomb forces, or magnetic domains by taking advantage of magnetic interaction. So, please do not forget that we are talking about a instrument which goes by the name atomic force microscope, and no way it is sort of limited to van der Waals force only or van der Waals interaction only. That is important to realize. In most cases or in most generically, irrespective of the material, the van der Waals interaction will be present, and therefore, the normal modes like contact mode, tapping mode, they primarily work with van der Waals forces. But the moment you have a setting where other types of interaction forces are also present, for example, Coulombic forces or the magnetic forces, they can also be utilized to identify different domains. So, let us say, in order to operate these two techniques, specifically the EFM and the MFM, we need a secondary circuit. So, what needs to be done in addition to the cantilever assembly, we need to have an electrical contact with the surface. Okay. So, through which a bias has to be given. So, typically a platinum wire is sort of drilled through a glass probe like this with an annular opening, through which the platinum wire is sent. So, I will draw it in greater detail. So, this is the probe now. It is a little bigger than a standard silicon probe, does not really matter. So, what it results is a little bit of loss of lateral resolution. So, this is how the probe looks like now. You typically insert a platinum wire or any wire, conducting wire, through this. and this is the surface. So, as it approaches, the wire physically comes in contact with the surface. There is, so the surface has to be a conducting surface, and you complete a circuit by applying a voltage or a bias from outside. So, in addition to this beam bounce probe etc., where the laser is operational like a standard AFM, you additionally have an electrical source, electrical circuit which supplies the bias. Okay. Now, what you do here is that you have to understand that this is a interaction curve based on pure van der Waals interaction. So, if there are other types of interaction, then what will happen, this nature of the curve might change. But what you need to understand that these Coulombic forces, for example, okay. So, these Coulombic forces, the electrostatic forces, have a much reduced decay characteristic as compared to van der Waals forces. So, let us say between particles van der Waals force is 1 by r to the power 6, we know that, and the Coulomb force is 1 by r square. So, even with understanding all this, if you do a scan with this probe as well as the circuit through which the bias is given along the contours of the surface. So, let us say this is the contours of the surface, and here you have some positively charged domains, here you have some negatively charged domains, something like this, and you give a, let us say, a positive bias. So, your tip is now positive. But if you still do a contact mode scan over here, you will still get nothing but the topography. If you, so this is the contact mode scan, and from this no way you can define that what are the different domains or the charge domains. And please understand, these are differently charged domains. So, they might not have a direct significance on a different adhesion or friction properties. So, the phase image might also be very, very blunt, it might not be able to pick up. So, what is typically done is, along with the bias turned on or the voltage turned on, you typically would do a non-contact scan also. So, if you do a non-contact scan, what will happen, it sort of follows the contours, but when it comes close to this area, since you have a positively biased tip and you have a positive electrical domain over here. So, there will be a local repulsion. So, instead of following the contour, it will sort of drift like this, and then again it is back. So, this part is neutral. So, there is absolutely no problem, it will follow. And what will happen over here? So, let us say this is the topography. You can get to this topography by doing a contact mode scan, or by doing a non-contact mode scan also by turning the voltage bias off. When you now do an additional scan with turning the voltage bias on, what will happen now? The tip is positive, this is negative. So, there will be an additional attraction. So, this area there will be a drift, this area there will be a drift, this area there will be a repulsion, and this area there will be an attraction. Okay. So, now when you superimpose these two scans, so the regular contact scan as well as the non-contact scan, what you have performed with a positively biased tip. So, this is the information you can get. So, one EFM scan. So, I will repeat what you are doing. You have a, instead of a regular tip, all you have is a glass tip with a, which is hollow. So, this makes it a little larger, nothing, no other harm, no other harm. So, it is like you just sort of take a tip with a, which is a little wider. So, that might lead to a little bit of loss in your lateral dimension, nothing more than that. This is mounted as usual on your cantilever, and all other properties remain the same. Only additional thing is you insert a electrical wire, platinum wire maybe, through it, and you apply a voltage, bias the sample. And then what you do, as a part of one scan of EFM, you first do a contact mode scan. Then you do withdraw the sample, withdraw the tip a little bit, and do a non-contact mode scan with an applied voltage. And you know that you have either positively or negatively biased the tip. You can bias the tip during your contact mode scan as well, but since at local proximity or in contact it is in the repulsive regime, the repulsive van der Waals, the repulsive component of the forces will dominate, and you will miss out any additional electrical signal. So, you are if you remember that when you are doing a contact mode imaging, you are over this zone. So, irrespective of whether you have a biased tip or not, these repulsion forces will, the local tip surface interaction forces will dominate, and therefore, you will miss out. So, when you do these two, and let us say you know that you had a positively biased tip, and then what you can find out from here is that a map of the domains, or the electrical conductivity domains. So, you know that you had a positively biased electrode. So, this part must be positive, because what has happened that over this area the non-contact scan shows a higher separation distance. So, this is possible only if there is a repulsive force between the additional repulsive force between the surface and the tip in this area. And what can be the cause of this additional repulsive force? You know that you have a positively biased tip. So, only if the surface at that particular location can have, or surface has a positively charged domain, then that can explain this additional repulsion. In contrast, here over this particular area, you see that there is some sort of an additional attraction between the surface and the tip, and this attraction can originate now that since you have a positively biased tip. So, therefore, it is only possible if you have a negative domain or negatively charged domain on the surface. So, that way you can sort of generate a local variation in the electrical property of a surface. So, this is what is done. So, this is often one single EFM scan involves two scans, and this is, you can understand the utility of non-contact imaging also. So, often you have to operate in the subtractive mode. Similar thing can be also possible for with a magnetic tip, with the application of a magnetic field, what is known as the magnetic force microscopy. It sort of images the spatial variation of magnetic forces or magnetic domains in a surface. MFM tip, so EFM tip, one has to use an electrical wire, so to make the circuit and make it conducting. And MFM tip, of course, it has to be coated with a ferromagnetic thin film. An image taking with a magnetic tip contains information about both topography and the magnetic properties of the surface. So, exactly in the same way one needs to know what type of tip one is using, whether it is N or S, and you might be having a surface topography with this type of different domains. So, you do a contact mode scan, and then you do a non-contact scan to find that there are certain zones where it is deviating. Okay. So, understanding that whatever was the magnetic property of the tip, there is an additional repulsion. And this is only possible if there is a local end domain over this surface area. Similarly, here you find that there is some attraction, and this is possible only when you have domains of different magnetism. Okay, so this is how MFM works. This is an interesting image of a hard disk, computer hard disk or a floppy disk. So, as I told you that if you do a simple topographic scan, you find that this is perfectly flat. So, there are no features, but if you now do an MFM scan, you can identify that there are magnetically active domains. Okay, so, this is in a nutshell the basics of magnetic force microscopy. The next thing is, of course, we move on to the last part of our discussion on AFM, which is the patterning application. What you need to understand that again during the rastering action, you are physically dragging the cantilever, the tip along the surface. And we have also talked somewhere during our discussion that during contact mode imaging, there might be possible meniscus formation due to condensation of water which is present in the surrounding. So, what happens is that as you raster or drag the tip along the surface, this water meniscus also travels along with that. So, one can use this water meniscus which forms, or one can artificially form it by controlling the humidity, that is also possible. Now, if certain molecules, let us say some SAM molecules, we already know about the SAM molecules, if they are sort of mounted on the tip. So, the tip, what you do is you just dip it before scanning in a layer of SAM. So, if you do that and then try to do a rastering scan following a contact mode, so along every line as the cantilever sort of, as the tip sort of moves, it is going to, this water meniscus is going to act as or going to deposit the SAM molecules onto the surface. And you know, we have discussed while talking about the microcontact printing, these SAM molecules, depending on the ligands X and Y, sort of orient and bind to the surface. So, in a way, every scan will result in very tiny but very uniform domains of SAM molecules, and the zones over which the cantilever has not scanned, there will be no deposition. So, this way you can sort of create very narrow lines of different wettability regions, which is known as the dip pen nanolithography, and up to 5 nanometer structures down to around 5 nanometer lateral resolution can be created by this. So, this is what you have to do. You have to just instead of a regular scan, because if you do a regular rastering, it is going to sort of cover the whole area. You have to just program the movement of your tip, and then so you allow your tip to move here, then sort of it skips 20 nanometers and then comes back here, then again skips 20 nanometers, scans here. So, you can in this process create 5 nanometer lines of a more or less wettable species depending on the nature of the SAM molecules you are using at a periodicity of 20 or 30 or 40 nanometer, whatever you want. So, you just need to program the movement of the scanner, and rest of the thing is perfectly fine. What typically is ensured that when you are writing, it's in the writing mode. So, you are not interested about the exact topography, and you want your surface, your tip to drag along the surface. So, generally during writing, the feedback loop is generally turned off, a specific force is set, and the cantilever is, or the tip is sort of ensured that the tip drags over the surface. So, this is what in a nutshell is dip pen nanolithography. So, here you can see we wrote something using silent molecules. Of course, this is a little wider, roughly about 80 nanometer width. So, there were multiple movements so that to make it visible. So, these are using SAM molecules, but more interestingly, what is important that you must realize that this image is not a topographic image, but it is a phase contrast image, because again if you write with SAM molecules, these are virtually feature heightless single layer molecules. So, the topographic contrast will be virtually very less. So, you can't pick it up in the topography, but this becomes visible in the phase contrast image, which you already understand. So, you see that AFM can also be used for writing for sort of something like nano writing. Okay, so these are some of the applications. So it can be used for nano writing, for example. Well, one of the classical approaches is to dip this AFM tip in a liquid SAM layer and then form this meniscus and then drag. One limitation is that it writes as long as the molecules are available. So once it writes a while or travels a while, all the molecules get exhausted, and then it may drag, but no molecules get transferred. So in order to overcome that limitation, something like called the fountain pen lithography came up, which uses the concept of this hollow probes, which we talked about while talking about this electrical force microscopy. So exactly using those hollow probes, and you just add a reservoir over which you dispense the ink. So the ink, due to capillary action, flows through this hollow probe, and this is now dragged or rastered along the surface. So all along it goes on depositing. So you don't really run out of the problem of running out of the SAM molecules. So it sort of uses an in situ ink reservoir, and one can sort of do a refilling also by dispensing a drop, which is a macroscopic entity over this zone. The disadvantage is that this is not compatible with all brands of AFM, and since you have to make them hollow, so the radius of curvature of the tip is higher, so the resolution is poorer. One can also use these concepts for let us say something like a tip induced field effect, tip induced oxidation on surfaces like silicon, titanium, tantalum, chromium, etc. So electron induced oxidation has also been applied to organic resists and something like that. So it is a combination of electrical force measurement and writing. So you just go to the appropriate location of the surface and then turn on the bias. Depending on the material and the reactants available, you can have localized oxidation when you turn on the bias. Other locations, if you do not turn on the bias, there is no reaction, so you can make very nice arrays of oxides on materials like silicon, titanium, etc. Of course, the last thing that is also possible with an atomic force microscope lies in the fact that during the approach and the debonding stage and the withdrawal stage. So withdrawal is something we did not mention, but once the scan is over, you will of course withdraw the tip from the surface. It actually follows the force curve. So utilizing that, one can measure the force between two surfaces, that is the tip of the cantilever and the surface you want to scan. So this we understand, this is the cantilever probe at a far away distance. This is jump to contact, then this is in the repulsive regime, and then you try to withdraw. What typically happens is that the withdrawal, the bonding, the attachment and the withdrawal stages are different. So there is a little bit of hysteresis between these two, the separation distance at which it jumps to contact and the separation distance. This is the separation distance between the Z piezo, the height of the Z piezo and the surface at which sort of it detaches. So this hysteresis or the gap in these two is a measure of the extent of adhesion of the surface. Weaker is the adhesion of the surface, lower will be the hysteresis. So weaker adhesion, lower will be the hysteresis. One can do these type of experiments with a standard tip, but it is generally customary to use the colloidal probes here. We talked about the colloidal probes. So colloidal probes find maximum application in finding out the measuring the forces between two surfaces. So it can have situations, for example, if both the probe and the surface are coated with some surfactant molecules of same species, there can be a situation where there can be a long range repulsion. So you do not see an attraction at all, and all the way you see a repulsive interaction. So this type of forces can be measured, this can be quantified, and this can sort of give you an idea about the adhesion of the surface as well as the nature of interaction between the surface, between the two surfaces. So firstly, by looking at the nature of the curve, one can find out whether the nature of interaction is attractive or repulsive, and second thing is, if it is attractive, one can find out the pull off distance, the extent of adhesion based on the hysteresis. Okay. So a whole lot of things can be done using an atomic force microscope. So that sort of brings us to the last slide, the last couple of slides of this class or this topic. The advantages of AFM. So one can achieve lateral resolution, allowing imaging and measurement of features on the order of a few nanometers, and the vertical resolution can be as low as 1 angstrom. 1 nanometer vertical height, of course, it is almost possible to achieve in any standard AFM. So, in situ scanning in different environments including ambient, that is the most important thing. So, if you are talking about any other high end microscope like a scanning electron microscope or a transmission electron microscope, they work only in ultra high vacuum. You need to have a significant vacuum, so that the electron clouds do not deviate because of collision with the air molecules. In AFM, nothing is needed. You can have excellent atomic force microscope scans in ambient condition. You can also have scans under liquid, at high temperature, at low temperature, almost anything and everything you want. So, that sort of opens up an avenue for a whole lot of in situ imaging. This is a non-destructive scanning procedure. So, you can look at your sample and then again reuse it for any subsequent experiment or subsequent processing. Materials properties. So, in addition to visualizing the topographic properties or the exact features, surface features, other material properties can also be quantified or directly measured using an AFM, which we discussed in this particular class in terms of the secondary imaging modes. So, you can have ideas like localized friction, adhesion, surface tension or contrast in that, as well as electrical and magnetic property domains by specialized techniques which we talk, like electrical force microscopy or magnetic force microscopy. One can measure viscoelasticity by force modulation microscopy, or the elasticity, the hardness, friction, magnetic domains, etc. Apart from imaging the surface, of course, as we have already talked, AFM can also be used to measure the extent of interaction forces or quantify the interaction forces between a surface and between two surfaces. So, one can look at the interaction forces between identical surfaces or by dissimilar surfaces by using colloidal probes, which are preferred tools for measuring the force, the interaction force for an AFM or between two surfaces. And then unlike STM, which we talked very briefly, you remember that STM requires a sharp conducting tip and a conducting sample to work. The AFM does not have any such limitations, and it works equally well for a conducting as well as a non-conducting sample or any type of a sample. So, polymer, ceramic, gel, liquids, everything can be sort of investigated with an atomic force microscope. And unlike traditional microscope, SPM systems do not use lenses. So, the size of the probe limits the resolution of your feature rather than the diffraction effects that typically limit the resolution in optical microscopes as well as in scanning electron microscopes. So, the same things, it is sort of a comparison of AFM with other classes of microscope or optical or electron microscopes. So, optical and electron microscopes can easily generate two-dimensional images of a sample surface with magnification as large as 1 million times for an electron microscope. But what is important, that these microscopes cannot measure the vertical dimension. So, none of these microscopes, irrespective of very, very high resolution, can give you a true vertical resolution or true 3D resolution. So, you can have a very clear idea about the feature size, the lateral size of the features, but that feature height, of course, in a scanning electron microscope, many of you have seen tilted images and things like that, but that really still fails to quantify the exact feature height, which is not possible to be produced in an optical microscope, and therefore, you cannot measure the exact depth of holes or height or pit or things like that. AFM, which uses a sharp tip to probe the surface, features by raster scanning, can image the surface topography with extremely high magnification and up to 10 million times, and that is not very important, but what is important is that you can see features which are laterally down to 1 nanometer or tens of nanometer is very, very easy to see, and vertically one can go down to 1 nanometer. And most important thing, the most fundamental apart from the operational aspect, AFM gives you a true 3D image. So, you have all the 3 dimensions, the x, y and the z accurately measured using an AFM. So, the last slide, some salient points in simple words. While you see in other microscopes you actually touch the sample in AFM, and the simplest and probably the biggest difference is you get a direct information about the topography and x, y and z directions. Okay. So, all the 3 directions which in all other microscopy irrespective of all their sophistication they are limited to x and y only. And since you have the ability to touch the sample, you can do things there, do things on the sample, which include you can pattern it, you can dispense it, you can indent it, or you can even dislodge molecules and do whatever you want to do. So, that is all I had to teach you in this particular course about the atomic force microscope. Please go through the lectures again and again and try to build your own concept. It's very simple. Apparently, it might be something new, but that's the whole intention of an advanced course, to expose you to newer developments, areas in which development is still taking place or which are really state of art. I would strongly encourage you to look into additional complementary literature. So, a search in the internet with the keywords like atomic force microscope, contact mode, tapping mode, intermittent contact mode, etc., should reveal you a whole lot of literature. And as I have repeatedly been telling, that in case if you have any doubt, do not hesitate to email me and I will be happy to answer any questions. Thank you very much.